All right, last bit of help with this lab. So in part 2, you're trying to figure out the normal force because we need to know the force between the surfaces to figure out the grippiness, as well as the force of friction, but we should already have that from part 1. So how do we get the normal force? Well, you'll notice on the left I've already drawn an FBD for when it's being pulled with a constant velocity to the right. So this is actually the answer for at least the FBD part of part 1. So if you do have something different, change it because this is the answer. So if you think about it, if it's moving with a constant velocity in the x, the spring force and the frictional force should be balanced. That was such a key part to helping us get the frictional force. But what we probably didn't look at yet was the y component, where weight is, of course, pulling your shoe down, and the table, which is the normal force, the surface force, is holding it up. When you drag this horizontally, it's not even moving vertically. So we should probably already know this and have seen this, but the normal force and the weight for this should be the same because it's technically in static equilibrium in the y component. It's not moving vertically. So if we can somehow figure out the weight of this shoe, Fg, remember that's weight, we then would be able to solve for the normal force by just setting up the sum of the forces in the y component equals 0, and again, writing down Fg plus Fn equals 0. How do we do this? Well, we've already done this actually. Again, think back to the first labs we did, the Hooke's Law lab and then the challenge labs, like finding the weight of objects. We didn't put it on the ground. We actually hung the shoe vertically from a spring, and it wasn't touching the ground. Why would this help us out? If you draw an FBD for when it's just hanging vertically, the weight, which is definitely going to help us over here to then get the normal force, the weight is pulling the shoe down and the spring is holding it up, and as long as it's hanging at rest, these should be balanced. So I can actually, before coming over to when it's dragged across the ground, I can actually apply Newton's first law to when it's being hung from the spring as well. So keep in mind this is going to be different than this, because this one is when it's hung vertically from the spring and is not on the table. This one's when I'm dragging it horizontally and it is on the table. All right, so if you think about it, with this one, it's not going to be friction. It's going to be, hey, there's a weight pulling it down and a spring force holding it up. And so if the missing piece to this puzzle is the weight, Fg, I've just got to somehow figure out the spring force. Well, you guys have already seen, as in part 1, you can do that if you figure out how much it's stretched from its original length, and then apply that stretch or displacement to Hooke's law with the spring constant. So we're going to actually use Hooke's law again. You won't get the same value you got in part 1 though, because this is not when it's dragged across the table horizontally. This is when you're hanging it to help you find this weight. Once you find the weight when it's hanging, the weight of an object will always be the weight of the object as long as its mass stays the same and it's still on Earth, which clearly we're not going anywhere else. So once you get this weight, you can actually then take it and apply it to Newton's first law over here, where we're looking then at Fg and Fn balancing out. All right, good luck everybody.